8.2, graphing f of x equals ax squared plus c. So in the last section, 8.1 was called graphing f of x equals ax squared. So this is going to be a parabola anytime this is going to be a quadratic function. And we looked at what happens when you have a coefficient in front of the x squared. Okay, so I'll review that in here. But now we're also going to be adding or subtracting something to the end of the function. Okay, so this says y equals x squared is graphed. Okay, so let's graph y equals x squared plus 2. So since we haven't added or subtracted anything to the end yet, let's just make an xy table. I've got some x's already filled in here, and let's just plug them into the equation. So if I'm plugging in 0 for x, then I've got 0 squared plus 2. That's 0 plus 2, so that's 2. Okay? When I plug in 1, I've got 1 squared plus 2. That would be 1 plus 2, which is 3. When I plug in 2, I got 2 squared plus 2. That would be 4 plus 2, which is 6. Okay, and then let's try the negatives. When I plug in -1, you want to do the squaring first, so this would be 1 plus 2, which is 3. Okay, and then finally when I plug in -2, I've got 4 plus 2, which is 6. Okay, so let's plot these points then. So 0, 2 is right here. 1, 3, and 2, 6. Oops, 2, 6 is right there, not right there. Sorry. And then I've got -1, 3, and -2, 6. Okay. And so, sorry, that's a mistake there, right? I meant that's supposed to be that point. Okay. And now when we graph this, you can see that this whole parabola has been moved up, right? If you plot the critical points from the original graph, maybe we should do that. Got the vertex there, here's 1, 1, and -1, 1, and then we'd have 2, 4, and -2, 4. So maybe you can see the whole parabola is shifted up 2 units, okay? So what this does, it translates everything up 2. A translation is when you shift either up or down or left and right. So this is going to be translated up 2. Okay. All right. So maybe you can guess what's going to happen then when we have a -3. But let's just try it out with the table. So I'm going to plot these critical points here first. So up 1 to the right 1, and then up 4 to the left and right 2. And that's because 2 squared is 4 and -2 squared is 4, right? Okay, so let's try out the table. I'm going to do these in my head this time instead of writing them all out, but you could. Okay, so I'm going to take 0 and square it. That would be 0, and then subtract 3. If I square 1, that's 1. Subtract 3 from that is -2. If I take 2 and square it, I've got 4, and then -3 gives me 1. -1 squared is +1, then subtract 3 and I get -2, and -2 squared is 4, subtract 3 from that and I'll get 1. Okay, so let's try plotting these. I get 0, -3, 1, -2, and 2, 1. And then going to the left, -1, -2, and -2, 1. And as you probably guessed, this is going to mean the whole parabola is shifted down 3 units. So when you have a positive number, it's going to shift your whole parabola up, and when it's a negative number, it's going to shift the whole thing down. Okay, so that brings us to vertical translations. Adding or subtracting a number from the end of a function shifts the graph up or down. That depends if you're adding or subtracting. Okay, so when c is positive, that means we'd be adding, and the graph is translated up. When c is negative, you could think of that as subtracting or adding a negative, and then it's going to move down. Okay? All right. So let's put this together with some of the transformations we looked at in the previous section in 8.1. So we're going to describe the transformations from the parent graph. I'm going to do that actually before I even graph anything. So this 2 that's going to give me a vertical stretch. Okay? And then the factor of that would be 2. Okay? And then the -5 is going to translate 5 down, or you can just say down 5 for me, but technically translate down 5. So that's my explanation of the transformations. Okay, so here's how I would graph this. Now you can make an XY table, that's totally fine, but what I'm going to do is first do the down 5, do the shift. So this is going down 5 units. That means my vertex is going to be right there. Okay. And then what I'm going to do is plot if this just is moved down 5 from the parent graph. I'm going to lightly put some other points, okay? So if there was no vertical stretch, let's pretend there's no vertical stretch. You'd go up 1 to the right 1 and up 1 to the left 1. And then you'd go up 4 to the right 2 and to the left 2. Okay, now those aren't my final points because I've still got the vertical stretch. But now what I'm going to do is take these points that I lightly did in pencil and I'm going to vertically stretch them. So I'm looking at these 2 points and they're 1 unit above the vertex. So I want to double that because my vertical stretch is by a factor of 2. So I want to double the height above the vertex. So you see now those points are 2 units above the vertex. Okay, so I was doubling that. And for the next set of points out, what I'll often see people do is they say, oh, I moved those points up 1 unit, so I'll move these 2 up 1 unit. But you don't want to do that. You want to double this height. So those points are 4 units above the vertex. So I want to double that. So I want to go up another 4 from here, which means up 8 from the vertex. So 1, 2, 3, 4. So this point will end up there. And that one point will end up there. So this is going to be twice as tall as the parent graph, in other words. Okay? And then we've got our parabola drawn. So it's really important if you're using this method to know the shape of the parent graph, because then you take these points and do your stretches and compression, stretches and shrinks on those. Okay? All right. So on this one, I've got this negative here. That means this is going to open down. So you can say opens down, or you could say reflection over the x-axis. But that's going to make it open down. Okay? Then I've got the 1/4, and I'm thinking of that separately from the negative. The 1/4 is going to give me a vertical shrink. If the number is more than 1, it's a vertical stretch. But if it's less than 1, it's a vertical shrink. Okay? And then the +4 is going to make everything move up 4 units. Okay? So I like to do the up 4 first, because that's going to tell me where the vertex is. So I'm going to go up 4 units. There's my vertex. Okay? And it's not going to move. And then my parabola is opening down. So I'm going to do this parent graph shape, but it's going to open down instead of up. So I'm going down 1 to the right and left 1, and I'm going down 4 to the right and left 2. Okay? Now this was what it would look like if the 1/4 wasn't there. If I just said y equals -x² + 4. But I still have to do the vertical shrink. Okay? So a vertical shrink, that means these points are going to move towards the vertex vertically. So they're going to move straight up towards the vertex. So since this is, our vertical shrink is 1/4, so the factor is 1/4. Okay? So that means I want these points to be just 1/4 of the vertical distance away that they are right now. So I'm going to take this vertical distance and divide it by 4, in other words. Okay? So this first set of points, I can see these are 4 units away vertically from the vertex. So I want to take 1/4 of 4. Well, 1/4 of 4 is 1. So that means those points would end up there. Okay? Then these two are just 1 unit away, so I want to take 1/4 of 1. Well, if you multiply 1 by 1/4, that's just 1/4, 1/4. So I'm just eyeballing 1/4 of a unit away from the vertex vertically. And then I'm going to have my graph. Okay, another way to handle these problems, you don't have to do this with using the parent graph shape. You could always make an XY table, right? So on this one, when I'm graphing this function, I would just use those same positions. I think, well, I want to know what happens when x is 0, 1, 2, and when the x is -1 and -2, and that will still give you these 5 points when you put those in, right? So I'd have 0, -5, just using the graph that I already made. This would come out to -3, and so would this one. And then these two would come out to +3. So that will still work with an XY table, and you can definitely do it that way too. Okay, they both work. So just to fill out the XY table here, using those 5 x positions. So 0, this would come out to 0, 4 if you plugged in 0 here. And then when you plug in a 1, I'm just using the graph here, this is going to come out to, this would be 3 3/4, so 3.75. And this would also be 3.75. Okay, and then when we plug in 2 for x, the y should come out to 3. Same thing with -2. Okay, so if you do the XY table, you'll get the same graph. That'll also work. Okay, so I think on the next page, maybe I'll use the XY table method. That might be a little more straightforward the first time you've graphed these. Okay, so let's see. We've got f of x equals 3x squared minus 1, and then g of x, a new function, function g, is going to be f of x with a 3 added to it. Okay, so we're going to describe the transformation from the graph of f to the graph of g. So I'm looking, well, what's the difference between f and g? Well, the g has f of x with 3 added to it, so this will shift. This means we're going to translate 3 units up, or shift 3 units up. Okay, so g is going to be translated up 3 units from f. Okay? All right, so let's graph the two functions on the same coordinate plane. So I'm going to start with f of x. So I'm looking at this. Okay, this means down 1. Okay, so my vertex then would be right here, and then this means this is going to be a vertical stretch. Okay, by a factor of 3. Whoops, I was off screen there. Vertical stretch by a factor of 3. Okay, so you could do this by stretching the parent graph shape up by a factor of 3, multiply those heights by 3. But you can also make an XY table. Okay, so let's do that. So for f of x, I want to use x values of 0, 1, and 2, and then -1 and -2. Okay, I'll just start with those. So when I plug in a 0 here, I'm just going to do this in my head. 0 squared is 0. Multiply that by 3, it's still 0. And then subtract 1, I get -1, which makes sense because I'd shifted my vertex down 1 unit. Okay. When I plug in a 1, I've got 1 squared times 3. So that would be 3 minus 1 is 2. Okay. When I plug in a 2, 2 squared is 4. 4 times 3 is 12. And then subtract 1 from that, 11. When I plug in a -1, -1 squared is 1. Multiply that by 3 is 3. And then subtract 1 is 2. And then when I plug in -2, -2 squared is 4. 4 times 3 is 12. Subtract 1 from that, 11. Okay? So let's try plotting this. We've got 0, -1. I already put that there. 1, 2 is right here. And then 2, 11 is going to be right here. -1, 2, and -2, 11. Okay, so this was function f. So I'm going to graph this. And then since there's going to be 2 functions on the same graph, I want to make sure that I know which is which. So I'm just going to write that that's f of x so I remember. Okay. So then for g of x, I'm not going to make an xy table for g of x because I'm just going to take that and shift everything up 3 units. You could do an xy table, but you'd need to write the equation first, okay? But I'm just going to take my vertex and go up 3 units. 1, 2, 3. There it is. Then I'll take this point and go up 3 units. 1, 2, 3. Same thing with this one. And I'll take these 2 points and move them up 3 units. 1, 2, 3, and 1, 2, 3. Okay. And then I'll draw this one in. So it's going to look very similar to the other function, just everything is going to be moved up 3 units, and this would be g of x. Okay? All right, so now let's write an equation for g. So we can't really do the xy table unless we have an equation. Well, let's think about this. They told us that g of x equals f of x plus 3. And I know what f of x equals because they say so right up there. F of x equals 3x squared minus 1. So I can take the quantity 3x squared minus 1 and substitute that in here for f of x. Okay, so I'm substituting in 3x squared minus 1 for f of x. And then I'm going to simplify this. Okay, so this would look the same without parentheses. So then I need to combine these like terms. And I'm going to get 3x squared plus 2. Okay, and now if you wanted to, you can make an xy table using this, and that would give you the points on the red parabola. Okay. Okay, next page. Zeros of a function. So the zeros of a function are going to be the x values for which f of x equals 0. Okay, so if I'm looking at these functions and I want to find the zeros, all I have to do is plug in 0 for f of x. Well, that's the first step. And then the second step would be to solve for x. So on this one, I'm going to add 10 to both sides. So 10 equals 2x, and then divide by 2, and x equals 5. Okay, so there is my 0. Okay, on this next one, I'm plugging in 0 again. Now this one, to solve for x, I'm going to use the zero product property because this is factored over here. So I've got something times something else equals 0. Well, either this or this has to equal 0 to make that work. So x plus 3 equals 0. Or x minus 1 equals 0. And so x equals negative 3 or x equals positive 1. So this has more than one 0. That's possible. Could have 3 or 4 or 7 zeros, could have any amount. Usually it's 1 or 2, at least at this point, but you could have more than that as well. Okay. All right, so moving on to this, this word problem. So an egg is dropped from a height of 144 feet. And here's a function to model that, okay? So the t is the time in seconds, and h is height in feet. And this is asking after how many seconds will the egg hit the ground, okay? So I'm going to take this function and graph it. Okay? You can actually just find the zeros. That will work too. But we can also look at the transformation. So the 144 means that this is going to be shifted up 144 units from the parent graph, right? The negative means that this is going to open down. Okay, and then the 16 is going to give you a vertical stretch. Okay, so let's see what happens here. So the vertex moves up 144, so I'm going to have to eyeball this. 144 is something like that, and then it's going to open down from there. Okay, so we're going to have a big vertical stretch, but you notice the scale on here. We can make an xy table. So I'd only be looking at x values, or t values I should say, of 1, 2, 3, 4, 5, and 6 if I did that, okay? But let's go ahead and actually find the zeros, okay? So I know that this is where the vertex is and it's going to open down from there, but let's just find where the zeros are, because I want if we're asking when is it going to hit the ground, well that means the height is going to be 0, okay? And the height is going to be f of t, all right? So what I'm going to do is take this equation and plug in 0 for f of t, okay? And then I'm going to solve this for t. So I want to get the t by itself. I'm going to subtract 144 from both sides. So now I've got negative 144 equals negative 16t squared. All right. And now I'm going to divide both sides by negative 16 to get rid of the negative 16. Okay. And let's just try that out real quick here. So negative 144 divided by negative 16 comes out to 9. So 9 equals t squared. Okay. So now I need something times itself is going to equal 9. Or you could take the square root of both sides. But the square root of 9 is 3. It's actually technically negative 3 as well. Okay. So t could equal 3 or negative 3, because negative 3 times itself is also positive 9. Okay, the point, that means one of my zeros is 3. So that means when t is 3, f of t is 0. So the point 3, 0 is on the graph. Okay, negative 3, 0 would be on the graph as well, but that doesn't really make sense because we're going back in time, right? For the time, we're only using positive times. So we're going to get a parabola that looks something like this. It's actually just going to be half of a parabola because we're not going to go into negative time. We're not going to go into negative heights either, right? But so we're only interested in this part. And you could plug in 1 and 2 for t to get the exact points of those, but it's going to look something like that. And this says after how many seconds will the egg hit the ground? Well, this is when it's going to be at a height of 0. So my answer is going to be 3 seconds then. Okay. All right, that's the end of the section, and I'll see you next time.